All right, so as we're getting ready for the review for the exam itself, let me just remind you of a couple of things. The final exam itself is 70 multiple choice questions and 110 minutes in length. Now, of those 70, I've already told you that about 62 are reviewed, stuff we've talked about this semester, and 8 we are going to consider as bonus. Meaning, by all means, take a stab at them. You've got a 1 in 4 chance of getting it correct just by guessing. You get it right, it adds to your score. You get it wrong, it doesn't take away anything. And that's going to be the case for all of them. You shouldn't leave a single question blank. There's no benefit at all. It's not like the SAT where a question left blank is better than an incorrect answer. Here we're talking literally, we're looking at a raw score. The higher that raw score is, the better your grade for the final exam will be. Now, in terms of the structure itself, what are the topics? We can find that the exam itself falls into these big categories. Atomic structure, and in atomic structure, you're going to find everything from just like the basic setup of the nucleus, all of this nuclear notation, isotopes, electron configurations, calculating atomic masses, orbital notation. We're going to get into molecular structure and bonding, where this is primarily Lewis structures, Vesper theory, being able to evaluate drawings, polarity, resonance, stoichiometry. So all the calculation-based stuff that we did, whether it's percent by masses, empirical formulas, converting between grams and moles and particles, doing solution-based stoichiometry, gas-phase stoichiometry, limiting reactants. States of matter, we're talking about chapter 6 kind of stuff. Intermolecular forces, the attractions between stuff at the liquid and solid phase. Looking at some of the gas laws, looking at how to make solutions. So how to determine the concentration, molarity. Looking at colligative properties in chapter 11, vapor pressure, molality, freezing point depression, solubility in water. Out of electrochemistry and redox, being able to determine oxidation numbers, being able to determine when oxidation and reduction are occurring. Remember, oxidation is the loss of electrons, oil. Reduction is the gain of electrons, Rid. Being able to assign oxidation numbers correctly. Being able to identify oxidizing agents and reducing agents. And then just some general kinds of descriptive chemistry related to periodic properties, things that you might have seen in lab. So those are the subcategories. Now, the one that isn't mentioned, the one that's got the 8 questions that we haven't done anything about, is thermochemistry. Now we've talked in lab just tiny little bits. We've used some of the nomenclature of thermochemistry. We've talked about this reaction is exothermic and this one is endothermic. This one feels hot, so it's releasing energy. That's exothermic. This one feels cold because it's taking in energy. That's endothermic. Now, those little definitions there might be enough to buy you 1 or 2 correct answers in that part of the exam. But again, don't worry about studying that stuff. That's bonus. It's not being held against you one way or the other. But there might be some terms that you have heard before, and you just kind of remember what those terms mean. It might help you get down to a 50-50 shot instead of a 1 in 4. And any little bit there helps. So with all of that in mind, I'm going to turn the review over to you now. We've got about 35 minutes. What are some things that we want to talk about? Some things that we've been kind of itching around with, struggling with, that we at least get started on that studying journey before Tuesday night, tomorrow night. No? Number 6, all right. All right, atom has a valence shell electron configuration of NS1. Where does it belong? Okay, so let's kind of just go through, let's break this down really quick. When we're talking about valence shell, what part of the atom are we talking about? We're talking about electrons. Where are those electrons? Are they close to the nucleus? Or are they far away from the nucleus? Yeah. Remember, valence electrons are the outermost electrons. They're the ones that are the furthest away. So what we're getting into here is, if we're talking about a valence shell configuration, another way of saying that is a noble gas configuration. Noble gas configurations are only concerned with those outermost electrons. So that's this first part here. Now, what does NS1 mean? Now, does anybody remember what N is? Yeah, it's the energy level. More precisely, we call it the principal quantum number. But that principal quantum number describes the energy level. So what we are saying is that we have a valence shell, an outer configuration of energy level S1. So we're talking about 1s1, 2s1, 3s1, 4s1, 5s1, and so on. Where would I find elements that had these configurations? Which group of the periodic table? Group 1. Remember, every configuration starts off with 1s1 or 1s2. 2s2, 2p6, 3s2. The first orbital, the first sublevel in any energy level is that S sublevel. It's the lowest energy. So the fact that we're talking about the first element in the first sublevel means we're talking about group 1 here. Now, what is the name of group 1? Well, we could throw out, we know it's not a transition element. All that stuff is in the D block. That's all in the middle. And the lanthanides, that's the F block. That's the stuff below the periodic table. Lanthanides and the actinides below them. So it comes down to, again, if you don't know that much, you probably can at least get this down to a 50-50. And 50-50 is a heck of a lot better than a 1 out of 4. So which one is it? It's the alkalis, it's D. Remember, the alkaline earth metals are so called because they are basic and they are found in the Earth's crust. Calcium, magnesium, strontium, those are your alkaline earth metals. So if the question was asking about NS2, that would be the alkaline earth metals. The alkaline metals, that is the first column, that's group 1. So that is a kind of question. Again, we're talking about multi-level definition kinds of things. Not only are we being asked to be good about our electron configurations, we're also being asked to be good about our common group names as well. Do you know where the halogens are? Do you know where the noble gases are? Do you know the difference between a main group element and a transition metal? Those little kinds of things, stuff that we kind of talked about in passing in chapter 3 when we did the entire periodic table in today. Those are the kinds of definition things that can kind of come up. All right, let's find another question to answer.
What section of the exam do most people struggle?
Okay, that's a good question. I would say that the area that probably gives the most problems is calculations. Any of the calculation problems, just because there are so many ways to kind of get lost. There's not a partial credit, there's not, so if we look at a problem like out of the stoichiometry section. Question like number 42 would likely give people a lot of trouble. And the reason is we didn't explicitly talk about how to do this, but you know how to do this. You just have never been asked to put the pieces together this way. So this is an empirical formula problem, 42. You're told that you've got this hydrocarbon, CXHY, it burns completely in the air, meaning oxygen, and it gives 18 grams, or excuse me, 0.18 grams of water, 0.44 grams of carbon dioxide. Now, one thing I want you to pay attention to here, test makers love to do this, and it is the values that you're being given here are not random. In fact, they're kind of telegraphing what it is that they want you to do. You know that the molar mass of water, we've done this enough times, is 18.02 grams per mole. And you're told that you've been given 0.18 grams. You know from experience that the molar mass of carbon dioxide is 44.01 grams per mole. And you've been given 0.44 grams. That relationship alone, knowing that this number and this number are very close to the masses that we are given, should tell us that carbon and hydrogen exist in the same one-to-one kind of ratio. So from that alone, A and D are going to be our options. Now, that being said, how do we go about solving this problem if we didn't know that information? Well, how we have to do it is this. Actually, I think I just spoke out of turn here, so I'm about to prove myself wrong. I make the same mistake you guys make when you make mistakes in stoichiometry. We can convert the grams of water into moles. Since we're looking for hydrogen, we need to turn the moles of water into moles of just plain old hydrogen. How many moles of hydrogen are there? How many hydrogens do I get out of every single water? 2. So here's going to be the difference. How many moles of carbon do I get out of every CO2? Just the 1. So I can do the calculation. That part's not a problem at all. I can even show you how to flub it up in your head. No problem there either. If I do the calculations, 0.18 divided by 18.02, it's going to give me 0.01 moles of water, which when I multiply that by 2 is 0.02 moles of hydrogen. 0.44 divided by 44.01, it's going to give me 0.01 moles of carbon, which would be, or carbon dioxide, which is 0.01 moles of carbon. So I can see here, I don't have a 1-to-1 ratio. This is where I made my own mistake, just assuming. This is actually a 2-to-1 ratio. My empirical formula is CH2. Now, CH2 isn't one of the options, but is there a molecule here that gives me that same 2-to-1 ratio of hydrogen to carbon? Yeah, it's B. So in a case like this, I'm going to revise what I said a few seconds ago. In a case like this, in which you have no way of getting the molecular formula because you don't have a molar mass, anything that has the same empirical formula could have been eliminated right off the bat. So it wasn't that A and D were the correct answers. It's actually that A and D were the ones that we knew had to be wrong because we had no way of discerning between them. They have the same empirical formula. And remember, the way we go from empirical formula to molecular formula is we need to know what the mass is so that we can know how many times to multiply that empirical formula to get the molecular formula. Without that information, I can't do it. So what am I left with? Well, I know it's not a 1-to-1 ratio. It's either a 2-to-1 or a 3-to-1. The math shows me it's 2-to-1. Now, we didn't do this kind of calculation. We didn't do this kind of analysis of empirical formulas when we looked at it in chapter 2. We did everything from that combustion analysis percentage standpoint. But understand, if you're given product information, you can work products back to reactants using stoichiometry. This is the thing that I was saying at the beginning of this problem. You haven't done a problem like this yet, but you know all of the tools. You have all of them there. We've done stoichiometry conversions ad nauseum from chapter 2, chapter 7, chapter 8, chapter 9. Now we just have a context, a new context to apply it. But empirical formulas are all about mole ratios. So if I can get moles of carbon and moles of hydrogen, I can figure out the empirical formula. It doesn't have to start at mass percent. But what I was saying here about the molar mass thing, you'll find that a lot, where they will intentionally give you masses that are easily divisible by the molar mass to make the math a little bit easier, a little bit less room for manipulation and interpretation. And this is certainly an example of that. So these kinds of questions probably give us the most problem on the exam, because at some level you feel the time crunch, because even though an hour and 50 minutes is a considerable amount of time, 70 questions in that 110 minutes means that, you know, do the math in your head. You only got a minute and change for each question if you do all the questions evenly and equally. And so my strategy always for exams like this is to go through the entire exam once. And as you are going through, just start filling in the results for the ones that you know. You got those concept questions, okay. Number 49 comes up. Limiting reactant in a particular reaction can be recognized because it's the reagent that would be used up first. Letter D, that's a definition question, doesn't require calculation, doesn't require manipulation, doesn't require any further thought. I just 49D, I move on. The reason I go through it that way is because if I can knock out all of those concept questions initially, and I know the answers, and I know I've probably got at least 3/4 of them right, if not more, then I can come back and say, okay, that took 20 minutes. I've got 90 minutes left to do the rest of this. And I can do the math and say, okay, I've now got 90 minutes to do 40 questions instead of 110 minutes to do 70 questions. I can feel a little bit better about my chances of finishing. I'm not quite as much under the same amount of pressure. If I just start at number 1 and I just start working through it, number 1, number 2, number 3, if number 1 through 10 are all calculations, and it takes me 45 minutes to do those first 10 questions, then I'm having a panic attack because I've got 65 minutes left to do the remaining 60 questions, and I'm starting to go, oh my goodness, I'm not going to finish. So literally the first thing I do when I get an exam like that, I'm going through it and I'm just starting to read through the question, and if it's something I know how to do, if it's something that's fast and easy, I'm filling in the bubbles as I go. I'm not getting bogged down in calculations. I'm not getting bogged down in concepts that I don't know. I can always come back to those. I can always guess on those later. I want to make sure I get through everything and that I'm not rushing to finish and making silly mistakes on stuff I really know how to do. The other common mistake that is being made is overcomplicating the symbol. Take a look at number 48. This is a simple question. It requires a single step calculation, converting the moles of one substance into the moles of another substance. But you will not believe how many times I get to people at the end of the exam and they've got a page and a half of calculations for a problem like this, because they've tried to convert it into Avogadro's number, they've tried to convert it to molar mass, they've tried to do a whole bunch of stuff, and none of the answers match up, or they get exactly where they were starting at the beginning. When all it is just looking at it and saying, oh, I'm going from moles to moles, 1.75 moles of oxygen. Every 3 moles of oxygen gives me 4 moles of iron. .75 times 4 over 3 is 2.33. It's a simple question, done simply. It's meant to be there for confidence. But because it's a high pressure test, because time starts to run out, sometimes you make it a lot harder than it has to be. So more often than not, rely on that first instinct. The first instinct is telling you, hey, this is a simple problem. Treat it as a simple problem. Look for a 1-step or a 2-step kind of calculation. There aren't going to be a whole lot of problems that are going to require an entire piece of paper to figure it out. Again, the test is designed to be done in a time window that is fast. So even the most complicated stoichiometry questions in here aren't going to be that involved. All right, we got about 10 minutes. Is there anything else that we want to talk about? All right, while you're thinking about that, let me buzz over here to the descriptive chemistry piece. Again, this is mostly stuff that you probably have seen in lab. And if not, they're relatively simple kinds of observational knowledge that they expect any chemistry student to know. So for example, why is aluminum useful for lining steel tank cars containing nitric acid? Well, there's only 2 answers here that really make any sense. It's not the first one. The first one sounds really smart, but has nothing to do. Yes, it does form an amphoteric hydroxide. That has nothing to do with transporting an acid. Because if it's a base, guess what? It's going to react with nitric acid. And the fact that it's a low density metal, again, really doesn't make any difference. It's true, but it doesn't make any difference. It's either C or D. It's either below hydrogen in the activity series and therefore unreactive with hydrogen, or it forms an oxide coating that the nitric acid can't break through. And it's actually the latter. Aluminum will react with acids in its pure metallic form. But one of the reasons we have trouble reacting with aluminum is because aluminum does form these oxide coatings. Which gas is the most soluble in water nitric? Trick question. Water nitric is another way of saying nitric acid. So what do we know about nitric acid in terms of its polarity? Okay. What do we know about water in terms of its polarity? It's polar. So which one of these is the most polar? I'll give you a hint. There's only one that is actually polar. Diatomic elements are not polar. They're diatomic. Their electrons are shared evenly between the two atoms. Methane, carbon and hydrogen compounds, we treat as nonpolar. So ammonia is the only logical answer there. It's the only one that's polar. So don't get caught up in the terminology. A lot of times the ACS will throw weird kinds of terms at you like this, or they'll talk about things like agua regia or something like that. Agua regia is a combination of acids dissolved in water. That's where the agua part comes in. It's Latin for royal water. Dissolves pretty much anything. If you're a Chem 106 student to be, you'll get to be very familiar with agua regia, because when we do quantitative analysis, qualitative analysis, it's basically the stuff we use to get our test tubes clean. Okay, what is the property of transition metals? Well, we know that they're not colorless. Think about copper solutions. Most of those are blue. Nickel solutions are mostly green. Cobalt solutions are mostly pink. Vanadium forms a whole bunch of variety of stuff. And even if we haven't seen any of those, we've seen iron in yellow and copper in blue. We know that colorless isn't one of the descriptors we use for transition metals. When we talk about nomenclature, though, this variability of oxidation number was the thing that we mentioned. That's why we have to put those Roman numerals on the names of all those ionic compounds. That's why we can't call it copper chloride. We have to call it copper 1 chloride or copper 2 chloride. The differences are because there are multiple oxidation states there. Questions like number 76. The formula of an oxide X is X2O3. What is the formula of the chloride of X? Comes down again to knowing our definitions, using them. We know that oxygen is a -2 ion. So 3 -2s would give a total of -6. X, since there are 2 of them, has to be +3 to give a total of +6. So if X is +3 and chloride is a halogen and it's -1, XCl3 has to be the formula of it, because X has to be +3 and the chloride's going to be -1. And then the remainder of these ones here are just periodic trends. Let's look at number 80 though. If the first 3 ionization energies of element X are 590, 1145, and 4912 kilojoules per mole, what is the most likely stable ion of X? So what we have to do, what is ionization energy? What happens when an ionization energy is added to an atom. We know it forms an ion. What kind? Well, we're adding energy. So if we're adding energy, what's happening to the electrons inside of the atom? They're going up in energy, up in energy, up in energy, until eventually they're so far away that one of them disappears. That's what ionization energy is. How much energy does it take to take an electron from the ground state and move it out of the atom completely? So we're talking about the transition from X to X plus to X plus 2, X plus 2, to X plus 3. Anything noticeable about these three ionization energies? They all seem to be varying about roughly the same amount. Or is there a jump? There's a jump. The second energy is a lot bigger, or I'm sorry, the third energy is a lot bigger than the second one was. These two are relatively close. The third one seems to be really far away. Now, when we see that, that usually means that we have transitioned from a higher energy level down to a lower one. The ones that are lower in energy are closer to the nucleus, they require more energy to get out. So if the first two ionization energies occur kind of normally, and then the third one is really big, that means that that third electron is coming from a different energy level, a lower energy level. So these were valence electrons. This was a core electron. There are only two valence electrons. Then we are talking about an alkaline earth metal. Alkaline earth metals have what kind of charge usually? +2. So in a question like that, that's really what you're looking for. Where is the jump in energy? That jump in energy tells us, okay, this is the line between valence and core. And I can just count how many valences there were, and that'll tell me what group it's in. Based on what group it's in, I can determine, okay, it had 6 valence electrons, so it must be in 16. It's an oxygen group. It's going to have a -2 charge. All right. Spend some time reviewing today, tomorrow. Bring more questions with you to the review session at 2. I'll see you there.